So you have studied electromagnetic waves, right? So those electromagnetic waves, if you see the equations which are very much complex. Now, if I want to implement such equations in real life or real this scenario, practical situation, it is very difficult. But that's why we can work out a simple model that is a ray-based model. We'll work with a simple model which is a far field theory or plane waves, and based on that plane far field theory and plane waves, we'll able to explain what exactly happens. Because if you go with this equations and all, it is very difficult to characterize or the practical situations to solve the closed system or closed formula for this particular problem. So antenna, if I consider that antenna which is a half wave dipole antenna, and it is transmitting the signal at all the directions. So if you see this particular wave pattern or radiation pattern of the antenna, we'll find that it is at the center. We can say that it is circular type circular things, right? So as the rays which are traveling far distance, what happens? It becomes a flat. It becomes a flat pattern. So antenna have a far field pattern, maybe directional or non-directional antenna, and the radiation pattern as the distance increases, so it becomes a flat. It becomes a flat. So we can consider a simplified model which is a ray-based model. Okay, here we can consider a ray-based model. So we can consider that electromagnetic wave that is transmitting in terms of a ray, in terms of a ray. Okay, so based on that, we have to study what exactly happens when a signal which is transmitted via this antenna and it is reaching up to the particular distance. What happens to the strength of that particular signal? Okay, so we have to discuss about that. So consider that when the wave which is propagated, when the wave which is propagated. So if you consider a scenario like a city, okay, there are different buildings, roads are there, some blockages are there, and the antenna which is transmitting the signal, some area that antenna covers. Okay, so what happens is the ray may get uh, there is a obstruction or there is a obstacles, we can say. So objects which the ray which is travel and which the ray which is get blocked. So the depending upon the surface of that object, multiple phenomena like reflection, scattering, diffraction that may happen to that particular ray, and the ray may change its direction. So if there are different phenomena like reflection happens if the surface is smooth, transmission through the object, or scattering of the rays and diffraction that may possible, right? So because of this, the ray may take different paths and it may reach up to the particular destination or the receiver by different path, right? So if you see this particular diagram, you will find that at the center there is a transmitter, for example. Okay, so if you are at the vicinity of that or within a line of sight of this antenna, what you will get directly the rays which that will come to your mobile or your receiver, and you can easily receive that particular signal. But at the same time, if something which is your signal which is get blocked, what will happen? So because of the building, so if you consider this is a building, and behind this building, whether it is possible to get this signal, you may not get direct rays behind this particular building, but at the same time the signal may get travel this point, it will get reflected back, and you may get some signal strength even though there is a block, right? Even though there is a block, but you will get some strength of the signal because of the reflected rays. Now, if you consider this far distance, far away from this transmitter, what will happen? There are different objects which are in between. There, the signal strength may get reduced, but still, weak signal the range that you will get at this particular location. So there are different phenomena, and because of that, the power of the signal gets reduced, and the coverage of that particular antenna may get hampered because of all these phenomena. So we have to discuss in detail about what exactly happens. So in free space, what happens? So ray tracing model, when we discuss about this, we start with a straight line of sight path. Line of sight path. So if you see this, this is a transmitting antenna, this is a receiving antenna, and the received signal r of t, which is given by this particular equation. So don't bother about the parameters. I will in a 1 minute I will explain in detail about that. So r of t, which is given by some real part of say lambda multiplied by root gl e raised to power minus j 2 pi d by lambda divided by 4 pi d multiplied by ut e raised to j 2 pi fc into t. So if you see this particular equation, you will find that the what is the input signal? Input signal is what? U of t is the input signal. Input signal is transmitted from the antenna is U of t. It is uplifted or the up converted by carrier frequency fc, means it is modulated. It is modulated, and we are finding what is the received signal strength at distance d. So d is the distance, lambda is the wavelength, and gl is the gain of the antenna. So now try to understand what exactly this gain of the antenna means. Suppose the antenna is transmitting the signal all over the directions, all over the directions, and it will transmit the power equally in all the directions, in all the directions. And say your antenna at your receiver, which is something a directional antenna in a specific direction, if you place your mobile or the antenna, you will get a maximum signal. So the gain is covered, or the range of that particular antenna, we can say it is limited because it is a directional, and because of that all this power which is transmitted by the transmitter may not capture. So it depends upon the aperture of that particular antenna. So antenna gain and all other parameters which are very very important over here. So we can say like that. Similarly, this parameter is a rotation. This parameter is a rotation. So as we are transmitting this sinusoid modulated signal over here, what happens is it completes number of rotation depending upon the distance and its particular wavelength. Okay, so if consider the case that if this mobile or this antenna which is moving, so this user may move, so this distance may change, and depending upon that the phase of this particular angle, phase of this particular signal, that may also change, and this parameter is related to the phase of this particular signal. So it is related to e raised to power minus j 2 pi d by lambda. So this is the phase of the signal, this is the gain of the antenna, lambda is the wavelength, and d is the distance between the transmitter and receiver, and fc is the carrier frequency, and u of t is the transmitted signal. So the received signal depends on the distance, depends on the rotation, that is a phase, that depends on, or distance dependent power decay. So as the distance increases, this power of the signal decreases, and wavelength plays a very important role at the transmitter, at the receiver antenna and its antenna pattern. So depending upon that you will receive the signal strength, that is r of t over here. So according, if you compute the power of this, how to calculate power? So signal square, right? So we square by r, or whatever I square into r, we can calculate the power of that signal. So squaring this. So Freeze law, what if free space equation? The Freeze law state that RPRX, that is the received power at the receiver antenna, is a combination. From this particular equation, we can say it's a combination of the transmitted power multiplied by the gain of the transmitter antenna, gain of the receiver antenna, gain of the transmitter and receiver antenna, both which are combined together, it is measured or represented as GL over here, right? So gain means how much power it is transmitting in this, in a specific direction, which is very very important, and based on that how much power that will reach up to the destination, that will depend, multiplied by lambda by 4 pi d square. So inversely proportional. So if your distance is increased, what will happen? The power reached up to the receiver antenna decreases. So this is a basic relation. So we can, if we compute this in dB domain, what you will get is summation of all. So dB of transmitted power, dB of transmitted antenna gain, dB received antenna gain, dB of this lambda square means 20 log, it will become similarly 4 pi and d. So all these parameters that will comes into picture, and this is the actual equation for the free space path loss. Okay, that is how much amount of the power which is received. So this is very important equation as far as this transmission of a signal is concerned. Okay, Is it clear to you or students? Any doubt up to this point?
No, sir.
Okay, this is a very
Yes, sir.
straightforward. This is very straightforward, and we'll try to model this some other things as well. So it's a basic model, that is a free space path loss model, we can say. Now we'll try to introduce one by one. If multiple rays means, if the signal takes multiple path, what happens? If a signal takes multiple path, what happens? So we'll discuss in detail about what exactly this two-ray model. So we have to extend, because we know that number of rays means the signal may transmit via the different paths. It may take the different path. But what exactly happens? So we have to slowly increase the number. So we'll start with just two ray. First is single line of sight path, and then two rays which are transmitted. So here, if you see the direct signal which is transmitted via this path, and another ray which is coming like this, it is reflected by the ground, and then it is coming to this particular receiver, right? So two paths are there. So same equation we can model using two rays, right? So the parameters are same. So this is a carrier, this x plus x dash and L. So L is the line of sight distance, x plus x dash is a distance covered by the reflected path, reflected signal path. So it is coming up to the ground, and then it is reflected back. So if this is happening, then what happens to this signal u of t? So straight away the signal whatever reaching up to the receiver, it is u of t. It is u of t. Okay. So same equation that we used earlier. Same equation. Next point is this u of t minus tau. This is very important. This is called as a delay. This is called as delay. Now there are two rays. So only two terms that you will get. Only two terms that you will get. If you are receiving a signal by n different paths, how many terms that you will get? You will get n different terms with n different delay components over here. So similarly, whatever I mentioned over there earlier, when I run that program, that simple code of convolution, what happens in that case? The signal which is get convolved with the impulse response, convolved with the impulse response. So all the effect which is coming at the receiver, okay, at a particular time is the current signal at a given time t, and its past values which are present in a system. Similarly, this in this case also the same thing which is happen over here. Same thing is happen over here. Okay, so everything, all the components are same, but there is some fluctuation over here. So we can say that if the received signal, or we can say that the signal received through the reflection and the signal transmitted as it is direct path, if they are in phase, what will happen? The interference, we can say the interference is constructive interference. If the phase difference is there, definitely your strength of the signal may get reduced. That is destructive interference. So these two terms are very important. So if you consider this particular graph, it is a function of log of d, distance log, and the received power. So what happens is somewhere here in this range, you are finding that there is some fluctuation, and again as the distance increases, the signal strength start decreasing. This is very important over here. So as d increases, your power goes on decreasing, and at the same time here fluctuations because of the constructive and destructive interference. So number of interference or number of rays that are reflecting back with a different path take different time to reach up to the destination, or destination means the receiver. And because of that, what is happening is the signal strength also get fluctuated, or it may get reduced or increased. So this is the two-ray model. Okay. So any question regarding this? Any
No,
question?
sir.
Okay.
So can you explain the graph once again?
Okay. So as the distance increases, this is a log. This is the log, right? And this is the received power. Received power. Now, if you see here, these are the two dotted lines mentioned over here, and you are finding that here there is a fluctuation in the signal. So the fluctuation in the signal is because of constructive and destructive interference of the signal, multiple paths. That is, the path which is coming over here, it takes different path, different length, and because of this, this phase will change. So this phase is important over here. That's what I mentioned here. That is a path rotation. Rotation means phase. Now, if you consider a sinusoid, a single sinusoid, okay, and if you add a same sinusoid with zero phase, what will happen? What will happen? Any
If phase is same, constructive interference over.
Constructive interference.
Now, if you consider that if the phase is changing, now I am making a phase is equal to say 45-degree delayed, 90-degree delayed, 180-degree delayed. So if it is 180-degree delayed means exactly out of phase. What will the addition of that two? So that's what, try to understand that constructive and destructive interference. So depending upon the signal which is reaching over here, it may fluctuate, okay, and it depends on the delay, so that within a specific distance, we can say distance versus that plot, you will find some problem in receiving that particular signal, right? So you can find out it's a relation. So at this point of time, don't go in detail about where actually it will happen to the as a function of d and all, but try to understand it constructive and destructive interference because of the multiple paths and rotation of the signal, this fluctuation in the signal. But as a function of time, function of a distance, if you consider as a function of d, okay, log of d, you will find that the strength of the signal decreases. It's a straightforward phenomenon. Okay, so we'll move ahead. So same diagram that I plotted over here. Now, if I extend to the 10-ray model, so there are different models which are mentioned in that book. Okay, so 10-ray model and then generalized model. So we'll not go in detail about all this, but we'll try to understand what happens to this 10-ray model. So when I'm considering that 2-ray model over there, so in that 2-ray model, what is happened is basically we are considering a single reflection, right? It is reflected and received up to the receiver. So it may happen that multiple reflection may take place. So which is indicated in this particular figure. So what are the situation mentioned over here? A line of sight means direct path from transmitter to the receiver. The ground reflected, so which is mentioned by GR, ground reflected. Single wall reflected, so reflected and straight away it is going to the receiver. Double wall reflected, so reflected from one wall, it is reached to the another wall, again reflected back and going to that. So this may takes place by multiple reflections as well. So similarly, triple wall ground, so wall ground and then reaching to the destination or the receiver. So multiple combination may possible over there. Okay, so what is the impact of that? So how to model this? So how to write the equation for this? So we have to consider all these effects by considering the individual delay in that particular environment. And when we say that multiple paths, okay, multipath and multiple reflections. So if the multiple reflection greater than 3, what happens? Every time the power will get absorbed by the material that where the actually the signal gets reflected, okay, or refracted, we can say. So in that case, what happens? Its strength goes on decreasing. So when it is multiple, more than 3 reflections, we can say we are not considering over here the signal which is of that strength. But again, it depends on what type of material or the object is there, which blocks that particular signal. So mathematically, we can easily write this equation, generalized case that we have seen earlier, that there are multiple one signal, that was the first model. Second signal, two ray model, the n is equal to 2, so only one component which are coming over there. And in that case, this second one is represented by u of t minus tau. Now if there are n number of rays, so we can say that it is 1 to 9, and the main ray, like line of sight, is totally 10 rays. So depending upon the environment, what we have to do is we have to model the signal. So it is u of t minus tau 1, u of t minus tau 2, u of t minus tau 3 with a specific distance x1, x2, x3, like that. You will get multiple reflections, and we can write the signal strength at this particular location. Okay, and generalized received power can be written by this equation. So don't bother about this equation. So just understand what exactly the meaning of each and every term. So again, the terms are same. So transmitter antenna again, receiver antenna again, rotation is there, distance is there, and multiple path of the signal. Okay, and now the very important term which is coming over here is narrowband model, which is narrowband model. So u of t is approximated by u of t minus tau I for all I. Then the received power is corresponding to the equation which is given in the next line. Okay, so just think about what is narrowband and wideband. So we'll come to this point later in the next couple of lectures. So this is a very important terminology. So this relates to the delay. So try to understand that this relates to the delay. Okay, so now if I use convolution, if I use convolution, like what you can say, with the delay which is in terms of say seconds, so half second, 1 second, 2 seconds, so you will find that clear echo signal that you will perceive over there. Okay, so how we are sampling, so depends upon how we are collecting the our data at the receiver, which is very, very important. So depending upon that, the same channel remains same, but depending upon the operation of the receiver, okay, the impact is different. The impact is different. So whether this delay will cause any effect, it depends upon your receiver and how you are receiving the signals. Okay, so if you consider a narrow band, even though this all the multiple reflection, don't bother about that, right? Because we are sampling at a specific instance, which is basically narrow band and wide band. So when we say wide band, means bandwidth is more, narrow band is bandwidth is less. So we can say narrow band means low pass channel. Okay, so we'll come to that point some time later, and we'll discuss in detail about what exactly the meaning, but try to understand this particular case. Now, these are the some important notings from this particular equation. So you can just go through this. What exactly happens is power fall off with distance, both 10-ray model. So urban empirical data and transmit antenna both above and below the building skylines, typically d raised to minus 2. So these are the different empirical models which are prepared, and based on that this data which is gathered over there and mentioned over there. So d raised to minus 2, right? More the fall of exponent is relatively insensitive to transmitter height. So there is no equation like the parameter which is considering the height of the antenna. The falloff with distance squared is due to the dominance of multipath rays, which decays at d raised to minus 2. So combination of line of sight and ground reflected rays with d raised to decays with respect to minus 4. So ground reflected rays, this is very important. So just note down this point, that ground reflected rays, the attenuation is more, and the factor which is d raised to minus 4. And empirical studies have obtained a power fall off with distance proportional to d raised to minus gamma. So this point we have to use in further lecture, next lecture, and d raised to minus gamma. So now, till now, whatever we have discussed, you can say that, so there may be multiple rays that are coming, and we have to find out. So we don't know exactly how many rays are there, how to model that particular received signal. Okay, and for that, empirical studies based on some data, transmitted power, how much power which is received, what are the characterization, building nature of that particular environment, and depending upon that, those studies which are very important, so those are called as empirical studies, empirical data. Okay, so it is very difficult that every situation, okay, suppose if you are considering in Bibewadi at Pune, some other location in village, or some crowded place, dense area. So the model should be precise to in that case. So it is very difficult to get all these, whether 10 rays model or 2 rays model, like that. But generalized case, how much is the data or the power which is received to the receiver. So based on the empirical studies, we have to come up with a solution, and that solution we can apply. So even though we have a great Maxwell equations which are present over there that you have studied in electromagnetics, in a constrained environment we have to apply those equation, and we have to solve that for a given conditions. Okay, and that is the empirical study which is very important in this particular case. What is the importance of this model? The importance of this model, which is if you consider the last line of this, okay, of this particular slide. So just local power, that how much power that is received by a particular receiver. So generally, we are considering that in specific location we are receiving a good mobile signal strength, but at a specific location we are not getting the strength. So the how much is the local mean received power, which is very important. So depending upon all these models, we can find out that how much area it can cover the particular transmission, and it's a very good indication to the link quality. So whether the link is properly will get established or not, and this is very important in cellular system as a function of power control and handoff. So this is very important that suppose you will study in mobile communication as well in further, that when the cell area, cell region, which is very small, and when you are reaching towards your, so you if you are moving away from that transmitter, what will happen, the signal strength from this particular model, signal strength start reducing. And when you enter into the another cell, when you enter into another cell, in case of a handoff mechanism, that your call should not get dropped, this how much power, minimum power required for the receiver to switch from one base station to the other base station, which is very very important. So in that case, your cell coverage area and transmitted signal power, received signal power, these terms are very very important over here. So we have to understand all these terminologies, and we have to use appropriate model for implement this particular wireless communication systems. And that's why what we are saying is empirical model. So earlier what we have discussed, that line of sight path, then 2-ray model, 10-ray model. So you can say n-ray model or a generalized multiple ray model you can present. But even though these models, exact data you will not get, because depending upon the environment the data get changed. Okay, and for that empirically we have to use some models. Okay, so most mobile communication system operates in complex propagation environment that cannot be accurately modeled by free space path loss or ray tracing. And in that case, these models are mainly based on empirical measurement over a given distance in a given frequency range and in particular geographical area. So important points to note here is how much is the distance, what frequency range that you are using, and what is the geographical area, okay, or a building. So these three parameters which are very important. And distance, we have seen that as a distance increases, your power decrease. Frequency, lambda is there. Okay, so as your frequency increase, your wavelength decrease. So definitely high frequency, your power will decrease. So try to relate all these parameters given in that particular equation. Similarly, geographical area will decide that model, that is 2-ray, 10-ray, n-ray model or generalized model. So depending upon that geographical area, your signal strength changes, and because of that you require some empirical studies and empirical model. Okay, so I will not go in detail about these two models, but note down this model, Okumura model and Hata model. These are widely used in mobile communication system, and these are empirical models. One is the graphical path loss data provided by Okumura, and other one is the empirical data which is provided by Okumura, and these models which are prepared. And these models are used in mobile communication. So the equations and everything which is given, equation for Okumura and Hata model, which is given in the textbook that I have mentioned, but not necessary to go in detail about each and every equation, but just prepare in brief that what actually the Okumura model is and Hata model, and what are the different parameters which are considered in that particular case. Okay, so these are very important things, and then we'll move on to the piecewise linear model. But now it is around 10:55, so we'll take this point in the next class, and before that we'll take questions if you have any questions. They are impacting the impact of other parameters on this particular transmission of a signal. Okay, so any questions regarding this particular lecture? So I request you to just so you can just register your uh, roll number and GR number, whatever name, GR number. Okay, in between that we'll take questions from the students. Okay, so now you can unmute your microphone and ask question, or you can just raise your hand, so I will give chance to that particular student. And I request you to just go through that videos, okay, and go through the book. So all the references which are given to you. So with once the lecture which is get over, just at least half an hour you spend, half an hour time you can spend. So around 1 and 1.5 hour within a week, if you spend on this, just brushing up what is discussed, what are the important points, and to solve one or two problems, we'll take those problems as well. So based on this, we can easily you can easily get prepared for the examination as well. So these are the very simple points we can say, but very important at the same time. So channel modeling is very important. So we are not directly going to the actual applications, but all these points which are very important studies, even though it's a theoretical aspect, but these are very important points. Okay, any question? So Niharika?
Yes, sir.
Any question?
No, sir.
So what I suggest is just go through those points that we have covered, and then we'll come back and we'll discuss in detail about the further points. And if you have any doubts, we'll cover those points as well. Pranav,
Yes, sir.
any doubt, or have you understood what is the importance of this channel characterization, channel modeling?
Yes, sir.
So even though it's a very theoretical aspect, but these aspects are very important. Okay, any other student? Chinmay, Chinmay Kolvankar.
Hi, yes, sir.
Any doubt?
No, sir. Not now.